Welcome back, children. In today's video, you will learn about ionization enthalpy, its definition. You will learn how to represent the values of ionization enthalpy. You will also learn about successive ionization enthalpies, factors influencing ionization enthalpy, and variation observed in the value of ionization enthalpy across a period and within groups, respectively. So, shall we move on to the class? Students, you must have learnt in chapter 2 that electrons jump to higher energy levels when you supply energy to an atom. Okay, likewise, if sufficient energy is supplied, electrons may be removed, resulting in the formation of a positively charged ion or cation. A quantitative measure of the tendency of an element to lose electron is given by ionization enthalpy. In short, it is written as IE. Okay, both should be in capital. I and E should be in capital letters. Ionization enthalpy is also known as ionization energy. Okay, enthalpy is another word for energy. Now, how is it defined? How do you define ionization enthalpy? It is defined as the minimum amount of energy required to remove the most loosely bound electron from an isolated gaseous atom in its ground state so as to convert it into a gaseous cation. It is represented by delta IH or IE1. For example, the ionization enthalpy of an element X is the enthalpy change delta IH for the process X gas gives X plus gas plus electron. Okay, when an electron is removed from X in its ground state, it resulted in the formation of X plus, a positive gaseous cation. Okay, here the enthalpy change delta H is given by delta IH or IE1. Here X gas represents the gaseous atom and X plus gas represents the resultant gaseous cation. Okay, it is the positive ion. If the value of ionization enthalpy or delta IH, you can also write it as IE1, is small, it means that only lesser amount of energy is required to remove the electron from the atom. Or in other words, it is easier to remove the electron from the atom when the value of ionization enthalpy is small. When the value of ionization enthalpy is large, greater amount of energy would be required to remove the most loosely bound electron from an atom. Clear? The values of ionization enthalpy are always positive because energy is always required to remove an electron from its atom. Now, what is the unit of ionization enthalpy? It is usually expressed in units of kilojoules per mole. Successive ionization enthalpies. After the removal of the first electron from the gaseous atom, it is possible to remove the second, third, and so on electrons from the resultant positive ions one after the other. So what is first ionization enthalpy? The energy required to remove the most loosely bound electron from the isolated gaseous atom is called its first ionization enthalpy. And this is represented by delta IH1 or IE1. Look at the process. X gas gives X plus gas plus electron. Okay, here an electron is lost. The enthalpy change or energy change associated with this process is equal to delta IH1 or IE1. Similarly, the energy required to remove the second electron from the resultant positive ion is called its second ionization enthalpy. This is denoted by delta IH2 or IE2. Clear? Delta IH2 or IE2 represents the second ionization enthalpy. Now look at the process. X plus gas loses an electron and forms X2 plus gas. Here the enthalpy change associated with this process is equal to delta IH2 or IE2. Now the energy required to remove the third electron from the resultant dipositive ion is called its third ionization enthalpy. This is denoted by delta IH3 or IE3. Here X2 plus gas gives X3 plus gas plus electron. The enthalpy change is given by delta IH3 or IE3. Thus, the ionization enthalpies required to remove first, second, third, and so on electrons from an isolated gaseous atom are called successive ionization enthalpies. A neutral gaseous atom X always has its number of electrons equal to the number of positively charged protons present in its nucleus. So initially, each electron of the atom X experiences equal attraction from protons in its nucleus. Now look at the process. X gas gives X plus gas plus electron. When an electron is removed from the neutral gaseous atom X, the positively charged ion formed, that is X plus gas, has one electron less than the number of positively charged protons in the nucleus. As a result, the force of attraction between the nucleus and the remaining electrons in the cation X plus increases. Now, each of the electrons in the cation X plus begin to experience greater nuclear charge, or in other words, they begin to experience greater attractive force from the nucleus. We can also say that the effective nuclear charge increases. Thus, the nucleus of the X plus ion would hold its remaining electrons more tightly. Therefore, greater energy would then be required to remove another electron from X plus. In other words, the energy required to remove the second electron from the neutral atom X would be greater than the energy required to remove the first electron from the neutral atom X. Now look at the process. X plus gas gives X2 plus gas plus electron. When an electron is removed from X plus, the dipositive ion X2 plus formed has one more electron less than the number of positively charged protons in its nucleus. Now, each of the electrons remaining in X2 plus would experience even greater force of attraction from the nucleus. Thus, the nucleus of X2 plus ion would hold its remaining electrons even more tightly, and consequently, the energy required to remove the third electron from the gaseous atom X to form X3 plus ion would be even more greater than the energy required to remove the second electron from X to form X2 plus ion. So this is why ionization enthalpies increase in the order delta IH3 is greater than delta IH2 greater than delta IH1. Or we can also write it as IE3 greater than IE2 greater than IE1. Note that for the process X gas gives X plus gas plus electron, where there is no mention of the first, second, third, and so on ionization enthalpies, the ionization enthalpy would be taken as the first ionization enthalpy. Now look at the enthalpy change delta H corresponding to this process. It is given as equal to delta IH. Here there is no specific mention about the number of the ionization enthalpy corresponding to this process. It is not specifically mentioned whether the value corresponds to that of first ionization enthalpy, second ionization enthalpy, third ionization enthalpy, and whatsoever it is. So in that case, we assume that delta IH is a value that corresponds to the first ionization enthalpy of the process X gives X plus plus electron. Now, there are various factors which influence the values of ionization enthalpy. What are they? Atomic size or atomic radius, nuclear charge, shielding or in other words screening effect of inertial electrons, penetration effect of electrons, and electronic configuration. So all these factors influence the values of ionization enthalpy of various elements in the periodic table. Let's learn how these factors influence the values of ionization enthalpy. The first factor which influences the ionization enthalpy of an element is its atomic size or atomic radius. Ionization enthalpy decreases with increase in the size of the atom. Look at the picture. In other words, ionization enthalpy decreases with increase in the atomic radius. Why so? As the atomic size increases, the electrons occupying the outermost shell lie at farther distances from the nucleus. Due to this, electrons in the outermost shell would experience less force of attraction from the nucleus. As a result, the outermost electrons are less tightly held by the nucleus. So it is easy to remove electrons which are less tightly held by the nucleus by supplying very less amount of energy, isn't it? Thus, ionization enthalpy decreases as the atomic size or the atomic radius increases. Now let us look at the second factor, nuclear charge. Ionization enthalpy increases with increase in nuclear charge. That is, it increases with increase in the number of positively charged protons in the nucleus. Okay, as the nuclear charge increases, the electrons occupying the outermost shell experience strong force of attraction from the nucleus. Consequently, the outer shell electrons are more tightly held by the nucleus. So it is not possible to remove electrons which are tightly held by the nucleus by supplying less amount of energy. Is it possible? Can you supply less amount of energy and try to remove electrons that are tightly held by the nucleus? No. Therefore, greater energy would be required to pull out the electron from its atom. Now look at the table showing the first ionization enthalpies of elements belonging to second period. You can see that the value of ionization enthalpy increases as we move from left to right of the period. This is due to increase in the nuclear charge observed in the elements lithium to neon. The next factor which affects the value of ionization enthalpy of an element is the shielding or screening effect of inner shell electrons. Ionization enthalpy decreases with increase in the shielding or screening effect of inner shell electrons in atoms. Or in other words, the energy required to remove an electron from an atom decreases with increase in the shielding or screening effect of inner shell electrons. Now, what's the reason behind this? In multi-electron atoms, the electrons in the outermost shell experience two kinds of forces. What are they? The first one is the force of attraction from the nucleus, and the second one is the force of repulsion from the electrons in the inner shells of the atom. We all know electrons are negatively charged. Okay, electrons in the outermost shell, they are negatively charged. Electrons in the inner shells are also negatively charged. So, we know like charges repel each other. Okay, so electrons in the outermost shell experience force of repulsion from electrons in the inner shells. So, these are the two kinds of forces experienced by electrons in the outermost shell of an atom. The net effect of these two opposing forces is that the force of attraction experienced by the outer shell electrons from the nucleus is a bit reduced by the force of repulsion exerted by electrons present in the inner shells. Clear? In other words, the actual positive charge felt by electrons in the outermost shell is called effective nuclear charge, Z effective. Okay, the effective nuclear charge is given by the relation Z effective is equal to total nuclear charge Z minus sigma. Okay, sigma is the screening constant. It considers the screening effect of electrons present in the inner shells. Clear? Now, the force of repulsion experienced by the valence shell electrons from the electrons present in the inner shells is called the shielding effect or screening effect. Obviously, greater the number of electrons in the inner shells, larger would be the screening effect. So, as the screening effect increases, the effective nuclear charge decreases. What do you mean by effective nuclear charge? The actual positive charge felt by electrons in the outermost shell decreases with increase in the screening effect. Okay, when there are greater number of electrons in the inner shells, the screening effect increases, as a result of which the electrons in the outermost shell experience very less force of attraction, or they experience less positive charge from the nucleus. Clear? So, as a result, the force of attraction experienced by the valence shell electrons from the nucleus decreases. This is the reason why ionization enthalpy decreases with increase in the shielding or screening effect of inner shell electrons in atoms. The next factor which affects the ionization enthalpy value of an element is the penetration effect of electrons. Ionization enthalpy increases with increase in the penetration effect of electrons. That is, for the same shell, ionization enthalpy would be more for s electrons than that for p electrons, because s electrons penetrate more towards the nucleus than p electrons. Okay, within the same shell, penetration effect decreases in the following order. That is, s electrons are more penetrating towards the nucleus than p electrons. P electrons are more penetrating towards the nucleus than d electrons. D electrons are more penetrating towards the nucleus than f electrons. Okay, now how does this affect the ionization enthalpy? Let's see. We know that in multi-electron atoms, electrons of the s orbital has the maximum probability of being found near the nucleus. Okay, we learned this in chapter 2. Remember? This probability goes on decreasing in the case of p, d and f orbitals respectively of the same shell. So, s electrons of any shell is more penetrating towards the nucleus than the p electrons of the same shell. The p electrons are more penetrating towards the nucleus than the d electrons of the same shell. Similarly, the d electrons are more penetrating towards the nucleus than the f electrons of the same shell. Now, if the penetration effect of the electron is more, it will be closer to the nucleus. Hence, it would be held more tightly by the nucleus. Therefore, ionization enthalpy will be very high. What do you mean by this? Energy required to remove or pull out this electron from the strong hold of the nucleus would be very high. We need to spend so much of energy in order to remove this electron from the tight hold of the nucleus. Hence, ionization enthalpy to pull out an s electron would be more than that required for a p electron of the same shell, which in turn would be more than that required to remove a d electron, and so on. In other words, ionization enthalpy would be more for s electrons than that for p, d and f electrons of the same shell. The fifth factor which influences the ionization enthalpy value of an element in the periodic table is its electronic configuration. Now let's learn the effect of exactly half-filled or completely filled orbitals. Atoms which contain extra stable electronic configuration. What do you mean by extra stable electronic configuration? Exactly half-filled or completely filled orbitals. So atoms which contain extra stable electronic configuration show high ionization enthalpy. That is, the removal of an electron from such an atom requires more energy than expected. For example, noble gases contain completely filled extra stable Ns2-Np6 configuration. Hence, greater energy is required to remove an electron from this extra stable configuration. Therefore, noble gases have the highest ionization enthalpy values in their respective periods. Variation of ionization enthalpy in the periodic table. Students, look at the graph showing the first ionization enthalpies of elements having atomic number up to 60. You would find that noble gases with completely filled stable electronic configuration are located at the maxima, right? That is, noble gases with stable Ns2-Np6 electronic configuration have highest ionization enthalpies. Alkali metals with one electron in the s orbital of their outermost shell have lowest ionization energy. Look, lithium, sodium, potassium, rubidium and cesium. All these alkali metals belonging to group 1 occupy the minima of this graph, isn't it? This is because it is easy to remove the electron from the outermost shell of alkali metals with lesser amount of energy. Hence, they are highly reactive. So, low ionization enthalpy values of alkali metals correspond to their highly reactive nature. You would also notice that in general, the first ionization enthalpy increases as we go across a period and decreases as we go down a group. This is shown by the green arrows. Now, let us consider the first period elements. What are they? Hydrogen and helium. Their first ionization enthalpy increases as we move from hydrogen to helium. Now consider the elements of second period. What are they? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Here also we can see that their ionization enthalpy increases as we move from lithium to neon. Okay, so this is the same trend followed by other period elements. Now look at the group of noble gases. Okay, noble gases are helium, neon, argon, krypton, xenon and radon. So as we go down a group from helium to xenon, we can observe that their first ionization enthalpy decreases from helium to xenon. Okay, similarly, if we consider the first group, the group of alkali metals, lithium, sodium, potassium, rubidium and cesium, here also you can observe that as we go down this group, the ionization enthalpy values decrease as we move from lithium to cesium. Why is this so? Let's learn about it. Now, let's first look at the trend observed in the ionization enthalpy values along a period. As we move from left to right across a period, for example, let's say from lithium to neon, we can notice that the nuclear charge increases, resulting in decrease of atomic size. Clear? As a result, the valence electrons are more and more tightly held by the nucleus as we move from left to right across a period. Consequently, more and more energy is needed to remove the electron and hence ionization enthalpies keep on increasing as we move from left to right of any period. In any period, the successive electrons are added to orbitals of the same shell. Okay, let us consider elements of second period lithium to fluorine. In these elements, the successive electrons are added to orbitals of the second shell. Okay, you can note that there are only 2 electrons in the first shell of all these elements. So, there are only 2 inner core electrons present in the elements lithium to fluorine. So there is no difference in the shielding of valence electrons from the nuclear charge by the inner core electrons. However, when we move from lithium to fluorine, there is an increase in nuclear charge. So there is a corresponding increase in the force of attraction experienced by valence electrons from the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding of the valence electrons by the inner shell electrons. In other words, force of attraction of the nucleus experienced by valence shell electrons due to increasing nuclear charge is greater than the force of repulsion experienced by valence shell electrons from the inner shell electrons which shield them. Hence, screening effect has less role to play in accounting for the increase in ionization enthalpy as we move from left to right across a period. Increase in ionization enthalpy across a period is therefore due to increase in nuclear charge resulting in decrease of atomic size. As a result, the valence electrons are more and more tightly held by the nucleus as we move from left to right across a period. Consequently, more and more energy is needed to remove the electron and hence ionization enthalpies keep on increasing across a period. There are some elements which show irregularities in this general trend. These are due to type of electron to be removed and extra stability of exactly half-filled and completely filled electronic configurations. Students, let us now deal with two cases that would help us understand the irregularities exhibited by certain second period elements. Case 1. The ionization enthalpy of boron is slightly less than that of beryllium, even though boron has a greater nuclear charge. This is due to the following reasons. Now, what is the electronic configuration of beryllium? Beryllium has an atomic number 4. So, it has 4 electrons in it, and the electronic configuration of beryllium is written as 1s2, 2s2. The electronic configuration of boron is 1s2, 2s2, 2p1 since there are 5 electrons in boron. The electronic configuration of boron is less stable than that of beryllium, which has completely filled orbitals. Also, the outermost electron in boron is present in 2p orbital, while in beryllium it is present in 2s orbital. Since 2s electrons are more penetrating towards the nucleus than 2p electrons, the 2s electrons are strongly attracted by the nucleus than 2p electrons. Hence, the 2p electron of boron is more shielded from the nucleus by the inner core electrons than the 2s electrons of beryllium. So, lesser amount of energy is needed to remove a 2p electron than a 2s electron. Hence, the first ionization enthalpy of boron is lower than that of beryllium. Look at the second case. The first ionization enthalpy of oxygen is slightly less than that of nitrogen, even though oxygen has a greater nuclear charge than nitrogen. Now look at the electronic configurations of nitrogen and oxygen. The electronic configuration of nitrogen is 1s2, 2s2, 2p3. Here, each of the 2p orbital is exactly half filled. The electronic configuration of oxygen, on the other hand, is 1s2, 2s2, 2p4. Here, the 2p orbitals are neither half filled nor completely filled. Since there are 2 electrons in the same 2p orbital of oxygen, there is more electron-electron repulsion in oxygen compared to nitrogen. So, that becomes easier to remove the 4th electron from the 2p orbital of oxygen. Since less energy is required to remove the 4th electron from the 2p orbital of oxygen due to greater interelectronic repulsion in oxygen, the ionization enthalpy of oxygen is less than that of nitrogen. Let us do an exercise problem 3.17. How would you explain the fact that the first ionization enthalpy of sodium is lower than that of magnesium, but its second ionization enthalpy is higher than that of magnesium? Let's account for the same. What do you mean by first ionization enthalpy? It corresponds to the removal of first electron from sodium and magnesium. What do you mean by second ionization enthalpy? It corresponds to the removal of second electron. Okay, we know the electronic configuration of sodium with atomic number 11 is 1s2, 2s2, 2p6, 3s1. And the electronic configuration of magnesium with atomic number 12 is 1s2, 2s2, 2p6, 3s2. In both the cases, though the first electron is to be removed from the 3s orbital, the nuclear charge of magnesium is higher than that of sodium. What do you mean by nuclear charge? It corresponds to the number of protons present in the nucleus. Okay, since the atomic number of magnesium is 12, there are 12 protons in its nucleus. So the nuclear charge of magnesium is plus 12. And the atomic number of sodium is 11. So there are 11 protons in its nucleus. So the nuclear charge of sodium is plus 11. So it is evident that the nuclear charge of magnesium is higher than that of sodium. Also, do note that ionization enthalpy is inversely related to atomic size of an element. Okay, since the atomic size of sodium atom is comparatively larger than magnesium, first ionization enthalpy of sodium is lower than that of magnesium. Also, the 3s orbital in magnesium is completely filled. That is, it has completely filled orbitals, while in sodium it is half filled. Okay, see the s orbital of sodium is which has a capacity of 2 electrons, has only 1 electron in it. So it is half filled, that is less stable. So the first ionization enthalpy of sodium is lower than that of magnesium because it is easier to remove an electron from a larger atom when compared to removing an electron from a small atom. See, sodium with electronic configuration 1:2:2p6 3s1 loses an electron and forms Na plus 1:2:2p6 in the first. This is the first ionization enthalpy. It corresponds to the first ionization enthalpy. Okay, now Na plus. You can see that the electronic configuration of Na plus is 1:2:2p6. This corresponds to the highly stable neon gas configuration. Okay, on removing a second electron from sodium, you get Na2 plus. See, the electronic configuration of the resulting ion, dipositive ion, is 1:2:2p5. Okay, now, after the removal of the first electron, Na plus gets the stable inert gas configuration. So, removal of second electron from sodium is difficult. Okay, now what about magnesium? The electronic configuration of magnesium is 1:2:2p6 3s2. Since the s orbital of magnesium is completely filled, it is comparatively more stable than sodium. So the first ionization enthalpy of magnesium is bit higher. Okay, so Mg plus is formed on removing an electron. So you get 1:2:2p6 3s1 as the electronic configuration of the resulting Mg plus ion. Okay, what happens on removing second electron from Mg plus? You get Mg2 plus with an electronic configuration of 1:2:2p6. Okay, here again 1:2:2p6 corresponds to neon gas configuration. Okay, so after the removal of the first electron, it is easy to remove the 3s1 electron from magnesium. So IE2 of sodium is higher than that of magnesium. Okay, so this is why the first ionization enthalpy of sodium is lower than that of magnesium, and the second ionization enthalpy of sodium is higher than that of magnesium. Students, work out question number 3.16, 3.18, 3.19 and 3.37 as your homework. Okay, question number 3.16. Among the second period elements, the actual ionization enthalpies are in the order given. Explain why beryllium has higher ionization enthalpy than boron, oxygen has lower ionization enthalpy than nitrogen and fluorine. And I've explained about this in this video, so you can listen, understand and write the explanation for the questions asked. Clear? Now, question number 3.18. What are the various factors due to which the ionization enthalpy of the main group elements tends to decrease down a group? So in this question you are asked to write down the various reasons for the decrease in the value of ionization enthalpy of main group elements on moving down the group. For answering this question, you must first of all know what main group elements are. What are main group elements? Elements belonging to S and P block are called main group elements. Okay, so you must write the various reasons for the decrease in ionization enthalpy of these elements on moving down a group. Okay, the next question is question number 3.19. The first ionization enthalpy values of group 13 elements are given. How would you explain this deviation from the general trend? You can see that there are certain deviations in the values, first ionization enthalpy values provided. You are expected to explain this deviation. Okay, I hope you would do that. Now, question number 3.37. You are asked to find out the incorrect statement among the 4 statements provided to you. So these are your homework. Hope you will do it before our next class. Now let's see how the values of ionization enthalpy vary within groups of elements. Now look at the graph showing the first ionization enthalpies of group 1 alkali metals. We can see that the ionization enthalpy decreases regularly with increase in the atomic number down a group in the periodic table. On moving down a group, the nuclear charge increases with increase in atomic number. So the force of attraction felt by the valence electrons is expected to increase. But this is not so in a group. Let's see why this is so. In a group, atomic size increases due to the addition of one new shell or one new principal energy level in each succeeding element. As a result, distance of the valence electrons from the nucleus increases, which is shown in the pictures displayed. Consequently, the force of attraction experienced by the valence electrons from the nucleus decreases, and this leads to a decrease in the values of ionization enthalpy down a group. Also, with the addition of new shells, the number of inner shells which shield the valence electrons from the nucleus increases. That is, shielding effect increases. Consequently, the force of attraction experienced by the valence electrons from the nucleus decreases, thereby leading to a decrease in the values of ionization enthalpy down a group. We can see that the combined effect of increase in atomic size and screening effect is greater than the effect of nuclear charge when we study about the variation of ionization enthalpy within a group. As a result, the valence electrons are less firmly held by the nucleus, and hence the value of ionization enthalpy gradually decreases as we move down a group. Question number 3.6. The first ionization enthalpy values of the third period elements sodium, magnesium and silicon are given. Predict whether the first ionization enthalpy for aluminium will be more close to 575 or 760 kilojoule per mole. Justify your answer. So, in question number 3.6, you are asked to find out whether the first ionization enthalpy value of aluminium is closer to 575 or 760 kilojoule per mole. Based on your prediction, you need to justify your answer. So first of all, let us write down the electronic configuration of all these 4 elements. Okay, so in order to write down the electronic configuration, you must know their atomic numbers. Only then it is possible for you to locate, have an idea of the position of these elements on the periodic table. Right? The electronic configuration of sodium with atomic number 11 is 1:2:2p6 3s1, and that of magnesium with atomic number 12 is 1:2:2p6 3s2. The electronic configuration of silicon with atomic number 14 is 1:2:2p6 3s2 3p2, and that of aluminium with atomic number 13 is 1:2:2p6 3s2 3p1. Okay, you can see that the ionization enthalpy value of aluminium will be more closer to 575 kilojoule per mole. The value of aluminium should be lower than that of magnesium because of effective shielding of 3p electrons from the nucleus by 3s electrons. Question number 3.15. Energy of an electron in the ground state of the hydrogen atom is minus 2.18 into 10 power minus 18 joule. Calculate the ionization enthalpy of atomic hydrogen in terms of joule per mole. Okay, in the second sentence, you have the unit joule per mole. So you need to apply the idea of mole concept in order to arrive at the answer for this question. Okay, so first of all, what is ionization enthalpy? It is the amount of energy required to remove an electron from the ground state to infinity. Okay, when you are pulling out an electron from an atom in its ground state, the electron is pulled out to infinity. Okay, the gaseous isolated positive ion is considered to be at infinity. Okay, the energy of an electron at infinity is 0. All this you have learned in chapter 2. Okay, energy of an electron in the ground state of the hydrogen atom is minus 2.18 into 10 power minus 18 joule. This is provided in the question itself. So what is the energy required to remove an electron in the ground state of one hydrogen atom? uh, you need to find out the difference between the two states. Okay, the energy of the electron at infinity minus energy of an electron in the ground state. When you do that, you get the answer 2.18 into 10 power minus 18 joules. Okay, we know that 1 mole of hydrogen atom is equal to Avogadro number. What is that? 6.022 into 10 power 23. So, the ionization enthalpy of 1 mole of hydrogen atoms is nothing but you multiply this Avogadro number with the answer you obtained in the last step, isn't it? What is that? 6.022 into 10 power 23 into 2.18 into 10 power minus 18 joule. On solving this, you get 13.12 into 10 power 5 joules as the answer. So 13.12 into 10 power 5 joule per mole is the ionization enthalpy of atomic hydrogen. Students, this is a different question. The first four ionization energies of an element X are given. Predict the number of valence electrons present in an atom of X. So you are asked to find out the number of valence electrons from the values, that is the four ionization energy values of an element provided. Okay, using these values we must arrive at the number of valence electrons present in an atom. Okay, the number of valence electrons can be determined by examining its successive ionization enthalpies one by one till a large jump in its value is found in moving from one ionization enthalpy to the next higher successive ionization enthalpy. Okay, so first of all, observe the ionization enthalpies IE1, IE2, IE3 and IE4. Look at the values. You can see that the considerable difference in the values of IE3 and IE4 show that the fourth electron is removed from an inner shell having stable noble gas configuration. Okay, so the number of valence electrons present in X would be 3. Students, this is a very important topic. Hope you will give due importance and learn it thoroughly. You can expect a lot of questions oriented in this topic in your entrance and in your exams. Okay, so do your best. Thank you for listening.